Okay, in the previous lecture we talked about the Turan's theorem. So what is the Turan's theorem? It's about the maximum number of edges in a graph without having kt plus 1 subgraph, right? Or in here we said maximum number of edges in a graph without kr subgraphs, right? Or kr plus 1 subgraphs. Yeah. Now, right, so the Turan's theorem the number of edges in a graph with no in a simple graph, no kr plus 1 subgraph, and we end up with getting an answer like this, where we have r sets, and between each pair is complete to each other, and each box is of a similar size, just differ by at most one. And this is something called the Turan graphs, TRN. And it turns out that this is the graph having maximum number of edges, having no kr plus 1 subgraph. Right? So sometimes we write ex of n kr plus 1, or let me say more generally, ex of nh is the maximum number of edges in an n vertex graph with no subgraph isomorphic to H. Right. So Turan's theorem is about the ex of n kr plus 1. Now, today we're gonna generalize that. So the first generalization is this Erzston-Simonovich theorem. It's actually quite a big generalization. So it states the following. Let H be a graph. Okay, I mean everything in this section is mostly simple graph. So let H be a simple graph. Then ex of nh is 1 minus 1 over chi of h minus 1 times n choose 2 plus a little bit of n square. Right. So what does this mean? So O of n square just means that it's a function, some function, such that f over n square goes to 0 as n goes to infinity. Okay? So in other words, if you replace this spot by, like, okay, I mean in other words, if you take an extremal number, x of nh, and subtract this 1 minus this number, then that's your function f, and that function divided by n square goes to 0 as n goes to infinity. Or you can think of it as some function who's, like, let's say n to the 1.9, something like that. It's sub-quadratic, right? N to the epsilon, where epsilon is less than 2, something like that. Or n squared over log n, or whatever. It's not n squared. All right. So this is the theorem. So if you plug in H to be the complete graph on r plus 1, if h is kr plus 1, then chromatic number of h is r plus 1, so then x of nh is going to be 1 minus 1 over r times n choose 2 plus some error term. Now, if you look at this thing, this is exactly the proportion of edges that are missing, or I mean that are present. Right? I mean, if you have an n vertex graph, number of edges is n choose 2, but among them, roughly one of r proportions edges are missing, because if I pick one vertex here and pick another vertex, the probability that the another vertex is not adjacent is about 1 over r, because the other vertex may belong to this spec with the probability 1 over r, but not exactly, right? There's some error. That error is taken care by little of n squared. Okay, so this is exactly, when H is a complete graph, and this describes what the asymptotic growth for the for the Turan's theorem. So At.the theorem generalized it fully. So for any graph H, the maximum number of edges in a graph having no subgraph isomorphic to H is determined by the chromatic number of H. So we're going to see the proof of that. Okay. Now, so how do we prove that? So to prove it, we will talk about some generic graph. Okay, so let me define KRT. Okay, what is KRT? Okay, let me just be same as Turan theorem. I will define KR plus 1T. So that's a graph where you have a r plus 1 backs of size t, so each of them has size t, and number of back is r plus 1, and between them it's complete. So in other words, you start with the complete graphs and complete graphs on r plus 1 vertices and replace each vertex by an independent set of size t. That is kr plus 1 t. All right. Why do we think of that? Because note that if H has chromatic number r plus 1, then H is a subgraph of kr plus 1 t for some t, right? Because you can choose t as big as we want, right? So if chromatic number is r plus 1, you have coloring by r plus 1 colors, and you look at the color class, having the maximum number of vertices, and take t as that number, and then your graph is a subgraph of the kr plus 1 t. So in order to prove the At.the theorem, it's enough to consider such a case. Later I will show you why. So that's the case that we will talk about. So let's first work on the simplest case. Okay. So what's the simplest case? The simplest case is, okay, so so let R is in this one, T is in this one, and then for every epsilon, there is big N0 such that if G is a simple n vertex graph with a large number of vertices, so n is bigger than n0, n has minimum degree bigger than 1 minus 1 over r plus epsilon n, then G has a subgraph isomorphic to kr plus 1 t, right? So that's the first dilemma we're going to prove. So for any epsilon, so r and t are constant, and for any epsilon we want to find a big number n0 such that whenever a graph has more than that number of vertices and has a minimum degree bigger than what we need, so like this, as Stone-Simonovitz theorem says that the minimum degree we need is something like this. Right? Minimum degree we want is like 1 minus 1 over r, and we want it to be slightly bigger, so 1 minus 1 over r plus epsilon times n. If that's the case, if the minimum degree is this, the number of edges is degree times n divided by 2, right? So if minimum degree is bigger than that, then it definitely has more edges than this number. So therefore, as long as n is big, you must, if this is true, you must have a h, which is ki plus 1 t, right? This is what we want. So let's see why this is true. Okay. So we're going to apply induction on R. Okay. So if R is 1, then kr plus 1 t is actually ktt. It's complete bipartite graph. In this case, actually, it's an easy lemma. So graph doesn't contain ktt subgraphs. So if I look at the vertex and its neighbor of size t, the number of pairs of vertex v and the set x of neighbors of size t, well, what is that number? Well, this number is at most, how big is it? Well, I can first choose t vertices. So this is when I sum over x. I pick a set of size t. And then these people have at most t minus 1 common neighbors. Right? Okay, so I should say, in the beginning I should say, suppose G has no ktt subgraph. So no t vertices have common neighbors, t common neighbors. So the number of pairs is strictly less than t times n choose t. Right? Can I just move that over here? Yeah. Yes. All right. That's an upper bound, right? So for every x, I have at most t minus 1 common neighbors, so it's t times n choose t. That's an upper bound. And for every vertex, how many ways do I have? For every vertex, I have a neighbor. So what's the degree, by the way? Degree of each vertex is bigger than 1 minus 1 over 1 plus epsilon n. So it's epsilon n. So degree is bigger than epsilon n. So n choose epsilon n, choose what? You gotta choose a set of size t. So that's what we have. Now we need some estimations. So n choose t. well, let's see. Okay, n choose t. Well, this is very rough estimation. N choose t is less than n to the t. Right? How about the other direction? And there is something like this. N choose k is at least n over k to the k. I'm using this inequality. So what do we have here? So n times n to the t times epsilon to the t, t to the t is less than or equal to t times n to the t. And if we cancel these things together, then what we end up is n is at most t times epsilon t, t to the t over epsilon to the t. So take, now it's over, right? Take n0 bigger than this number. Then we win in if r is 1, right? This means G has a KTT subgraph. All right, so that's the proof for the easy part when r is 1. Now, more difficult part is when r is bigger than 1. So now assume r is bigger than 1. Okay. Now what's going to happen? Now we apply induction. So by the induction hypothesis, this is induction on R, so we're gonna get the KRS. G contains KRS subgraph for some S bigger than T as long as n is big, right? Because this is 1 over 1 minus r plus epsilon, and it's bigger than 1 minus 1 over r minus 1 plus epsilon n, right? Now here note that we chose S to be something. I'm gonna choose that later. So we have a KRS. So right. So G has disjoint vertex sets A1, A2. AR, each of them has size exactly S, and between them it's complete. For all I less than j, every vertex in AI is the adjacent to every vertex in AJ. Right, so this is precisely what we mean by having KRS. So the size of this is S. Now our goal is to pick B1 as a subset of A1, B2 as a subset of A2, and BS as a subset of AS. It's not S actually, it's R, right? Such that each of them has size exactly t, because we want to find the kr plus 1t, and b1 g, there are at least t vertices not in union of AI but adjacent to all vertices of union of BI. Right? Because why? If that's the case, if we have a B1, B2, B3, BR, and if you have enough number of vertices outside which is complete to everybody, which is adjacent to everybody, then we will get a KR plus 1T. The size of this is T. Okay, so this is the goal. So how do we make sure that such a thing exists? Right. So let W be the set of vertices of U, which is VG minus union of AI, such that it has at least T neighbors in each AI. Right, so here you have A1, A2, AR, and W is a set of people having at least T neighbors in everything. And outside of W, you have the opposite. So you have some AI where that vertex has less than T neighbors. Now, everybody here has somebody where you have too many non-neighbors, right? So thus, each vertex in U minus W has some I in 1 up to R, such that, okay, but this is V, then V has less than T neighbors in AI, meaning that more than S minus T non-neighbors. In AI. All right, now I'm going to count number of pairs of such a thing, right? So number of pairs of V and W, where V is in U, W is in the union of AI from 1 up to R, and VW are non-adjacent. How many pairs do we have? Because of these previous observations, you gotta have, so if I pick somebody, so that's U minus W, so for every vertex outside of W in U, each of them will have at least S minus T non-neighbors in each set AI. I mean, not each set, for some set AI, right? So the number of pairs that they are non-adjacent is bigger than that, But on the other hand, each vertex is degree something, right? So the degree of W is at least 1 minus 1 over R plus epsilon n for all W in the union of AI. So the number of non-neighbors of W is at most 1 of R minus epsilon n, because the degree plus, number of non-neighbors is n minus 1 minus degree, right? So definitely it's less than that. And so for every vertex we are adding this, so 1 minus R epsilon n, so that's the degree. And then the size of union, so number of vertices that we are counting for W is R times S, right? That's R times S vertices here. All right, so now we have some equations. Now let me see what we get. So note that size of U is n minus Rs. So n minus Rs minus W is less than S minus T, 1 over S minus T, and 1 minus R epsilon n Rs. Right? Yes. So W is greater than or equal to W is greater than or equal to n minus Rs minus, okay, so let's work with this way. So n times something minus Rs. So what is the coefficient of n? This S minus T and 1 over R minus epsilon, Rs minus 1. Am I doing all right? No, the other way around, right? Okay, so U minus W S minus T is less than or equal to that. So W is at least W is at least 1 minus 1 over S minus T, 1 over R minus epsilon Rs, right? And we want W to be big if n is big. How do we make that happen? Well, since this is a linear function as a function of n, because if I fix epsilon R T, then everything is fixed. I have a freedom to choose as I like. So we want W to be big, so that means 1 minus S minus T, 1 over R minus epsilon Rs. We want this to be positive, right? Then if n is big, this will be big. So what does that mean? That means S minus T is bigger than this. So S minus T is bigger than S minus epsilon Rs, right? So what do we get? So we need epsilon R to be bigger than T. epsilon rs to be bigger than t, so as long as s is bigger than t over epsilon r, then the coefficient will be bigger than 0. Okay, so for instance, take s to be t over epsilon, and we want something like this because we want it to be integer. Okay, if this is the case, then w is big as long as n is big. So we can choose n0 to be big enough so that this is big enough. All right. Now that's good. The reason why this is good is because now I know that this set is big. So I have many vertices each having t common neighbors. So the number of choices of t neighbors in each AI is exactly what? Right, S choose R and R, right? S choose T to the R. So what does that mean? So if W is bigger than T times S, this number, then there are at least T vertices in W having the same T neighbors in each AI, right? So that implies that you have a B1 up to BR, right? This gives me B1 up to BR. Now take W, BR plus 1 to be a subset of W whose size is T. Then we have a KR plus 1 T as a subgraph. Okay, so how do we know that this is true? Well, as long as n is big and s is something like, right? Oh, how do we know? I mean, t as choose t to the r. This is the number, and everything is fixed, right? S is fixed, x is given as a function of epsilon and t, so this is constant, right? So if n is big, w will be big enough so that it's bigger than this number, and therefore graph will have a kt plus 1 t as a subgraph. So that's our first lemma. That's the weakest case, right? If minimum degree is big, then you must have a complete graph, the blow up of a complete graph as a subgraph. Now our second theorem is called At.this Stone. Sometimes called At.this Stone theorem. In 1946, it's a bit earlier than At.this Stone-Simonovich theorem, and it says that what we expect for every epsilon there is n0 such that if the average degree of G is at least 1 minus 1 over R plus epsilon, number of vertices of G is bigger than 0, then G has a kr plus 1 T subgraph. Okay, so instead of a minimum degree, now we are slightly more general and we want it to be average degree. And the proof is just to reduce to the previous lemma. How do we reduce it? The goal is to find a subgraph whose average degree is bigger than 1 minus 1 over r plus epsilon over 2, and number of vertices is also big. This is what we want. Okay, how do we find it? Well, we repeatedly delete a vertex of degree at most 1 over 1 r minus r plus epsilon over 2. And okay, now we keep repeating, keep deleting those vertices. Eventually the process must stop because the graph is finite. You cannot delete forever. Right. So in other words, let gi be a gi plus gi be a gi minus 1, delete vi minus 1 if degree in gi minus 1, vi minus 1 is less than or equal to 1 minus 1 over r plus epsilon over 2, and number of vertices of gi minus 1. Does that make sense? Right, so we keep deleting vertices and then we end up with the graph. The process must stop because eventually the graph will be too small. Right, if you have one vertex, you never delete anymore any further. Okay, now how many edges do we remove? Each time, whenever we delete a vertex, we delete small number of edges, right? So let's say v of h is h, right? So initially I had the n vertices, so this is like from h plus 1 up to n. We deleted like 1 over 1 minus r plus epsilon over 2 times I. Right? So, am I doing all right? So this is like 1 over 1 minus r 2, and then we have like m plus 1, no, h plus 1, h plus 2, up to n. So that's the number of edges that we remove. Okay, so how many is it? So 1 minus 1 over r plus epsilon over 2 times n minus h plus So we are summing from 1 up to n minus h. So this is the sum, right? That's the number of edges that is removed. So the number of edges of the whole graph right. Yeah, so number of edges of the whole graph. I know by the average degree argument this was average degree, so the number of vertices is n, so degree times n, so that's number of edges, so half, right? That is number of edges. And for the upper bound, we start with the number of edges of h, right? Number of edges of h plus number of edges that we have deleted. So 1 minus 1 over r plus epsilon over 2. And okay, what is this? Anyway, I'm lazy, so let me just copy same thing. All right. So what is that? Number of edges of h is equal to, at most h choose 2, and then this times m minus h squared over 2 plus 2/3 m minus h. Right, this is what we have. Now we can look at these two inequalities, right? What do we observe? You have some common terms actually. So this is h squared over 2. Now h. Okay, let me not fix it. H choose 2 minus 1 over r plus epsilon over 2 times n squared over 2 minus 2hn over 2 plus h squared plus 3 over 2n minus 3 over 2h. Right, so now I can cancel these two terms, right? So that means h choose 2 plus 1 more this number right, h squared minus h minus h minus plus 3 over 2h plus 3 over 2n. This is bigger than 0. All right. Now, how big is it? All right. Now it's a matter of computing things, I think. But there may be an easier way. Am I cheating or not? It's h squared. Yeah, this is anyway quadratic function. And if h is equal to no. even though it's a bit dirty, let's just compute. Alright. H square over 2. Oh, now I realize, so there's a 2, okay? Right. I just need to make sure that H is big, if N is big, because right, in order to satisfy this, why is H big? And should I just continue? H square over 2 minus H over 2 plus H square over 2. Something's strange. Oh, that has been, yeah, this is not right. So if H is oh, I now realize where I made a mistake. So this is N, right? NH. So I wrote it as a function of H, right? So H squared in oh, all right. It's not really important, probably. Right, it's 2 and H squared plus 3 over 2 times N, yeah, minus 3 over 2 times H. All right. Yeah, so how do we make this to be big? So we just, I think it's a matter of computing. If H is something like, yeah, so we want, if N is big, then H is big too. Okay, Y all right, so let me just rearrange. So okay, something like this. H squared, so 1/2 plus 1 minus 1 over r plus epsilon over 2, and then just little terms like half h is bigger than minus minus okay, half, and then yes, minus yeah, okay, 1 minus 1 over r plus epsilon over 2. Oh, I see. Minus 1 minus 1 over r plus epsilon over 2, n plus 3 over 2, plus half h, plus 1 minus 1 over r plus epsilon over 2. Do we really have to do this? But anyway, so this is a coefficient which is something. So this is positive, this is positive, and this is negative. So if we draw this graph, right, when h is 0, is somewhere here, and then it looks like this, right, as a function of h. So I claim that the h will initially when h is n, it should be somewhere here, right? And as soon as the inequality is violated, it will be stuck. So that's when this is happening. So that means h will be big, right? H will be bigger than, for instance, h will be bigger than that, right? H will be bigger than like, what is it? 1 minus 1 over r plus epsilon over 2, n plus 3 over 2, half divided twice, 1/2 plus 1. Okay, I'm just writing whatever, right? H is bigger than that if we do this process. So that means if n is big, then h is big. Okay. All right, so what does that mean? That means we can find the subgraph, right? We find the subgraph whose minimum degree is big. Once we find the subgraph whose minimum degree is bigger than this, with epsilon over 2 here, we apply the previous lemma to deduce that there is a complete graph, blow up of complete graph. Okay, so that's the proof of At.this done. Now finally, let's prove the proof of the Erdős-Stone-Simonovitch. Okay. Now it's easy. If h is chromatin number is r plus 1, then h is a subgraph of k r plus 1 t for some t. So that means the maximum number of edges in a graph without h what is it gonna be, right? If it doesn't contain kr plus 1t, the maximum number is at least this. And the Turan graph doesn't have a kr plus 1. Oh, no, the other way around. Yeah, so any graph, okay, so any graph that contains below of a complete graph contains h. And the Turan graph doesn't contain any subgraph of chromatic number r plus 1, so this is the situations. Now, what does that mean? That means and actually both of them are actually about 1 over 1 r and choose 2 plus little n square, right? So that means this is sandwiches in between, so it's 1 over 1 minus 1 over r n square and choose 2 plus little of n square. All right, so that's the proof. Right. Now, let me tell you some stories about this. So Eddy-Stone's monophysity theorem precisely determined the growth rate of the maximum number of edges in a graph without fixed graph h. But here's the problem. If h is not bipartite, then it's okay. Then chromatic number is bigger than 2, so basically this is about 1 minus 1 over r. The chromatic number determines, right? And this is non-zero. But if chromatic number of h is 2, then this is 1 minus 1 is 0. So what it tells you is that this is 0 plus 0 times n choose 2 and little o square. So that just means it's a subquadratic and it doesn't tell you anything else. So that's the big problem. So the bipartite trap problem remains very much open. So we fix graph h, bipartite graph h, and to determine the maximum number of edges graph in a graph without this h subgraph. Let me tell you a little bit. So like the growth rate, what is growth rate of x and h if h is bipartite? And it's known that each of them is something like n to the zeta where zeta is some number between 2 and 1. Okay, less than 2. And precise number growth rate is known for only small cases. So for instance, complete bipartite graphs with one side way bigger than the other side, or even cycles for a small number of even cycles, only 3. So even for K44, we have no idea about the growth rate, or C8, or three-dimensional cube. So my former PhD student Dong-Yap Kang with Jae-hoon Kim, Dong-Yap and Jae-hoon made a theorem stating that the set of points that can be realized as this exponent can be, there's a conjecture that any rational number can be exponent of some bipartite graph, and they prove that those points have limits. Okay, there are infinitely many points having convergence of a sequence. Anyway, people study this kind of problem a lot. Let me tell you one more conjecture. Okay, so the conjecture by At.the and Simonovitz. And this conjecture has price $100 due to At.the. So if you solve it, then you may get a price. So if H is bipartite and every induced I don't know whether I remember correctly, maximum degree and most are, then number of edges in a graph without that is so I'm not gonna explain the big O notation. Basically, you have to prove that the extremal number divided by n to the 2 minus 1 over r is bounded, and it's known. What's known is x of nh is O of n to the 2 minus 1 over 4. This is like Alon, Krivlevich, and Sudakov. And there may be other theorems known. Okay, so that's it for today. In the next lecture, we will talk more about extremal problems.